Concrete is the most widely used construction material in the world. It can be found in swaths of city pavements, bridges that span vast rivers, and the tallest skyscrapers on Earth. But this sturdy substance does have a weakness. It's prone to catastrophic cracking that costs tens of billions of dollars to repair each year. But what if we could avoid that problem by creating concrete that heals itself? This idea isn't as far-fetched as it may seem. It boils down to an understanding of how concrete forms and how to exploit that process to our benefit. Concrete is a combination of coarse stone and sand particles called aggregates that mix with cement, a powdered blend of clay and limestone. When water gets added to this mix, the cement forms a paste and coats the aggregates, quickly hardening through a chemical reaction called hydration. Eventually, the resulting material grows strong enough to prop up buildings that climb hundreds of meters into the sky. While people have been using a variety of recipes to produce cement for over 4,000 years, concrete itself has a surprisingly short lifespan. After 20 to 30 years, natural processes like concrete shrinkage, excessive freezing and thawing, and heavy loads can trigger cracking. And it's not just big breaks that count. Tiny cracks can be just as dangerous. Concrete is often used as a secondary support around steel reinforcements. In this concrete, even small cracks can channel water, oxygen, and carbon dioxide that corrode the steel and lead to disastrous collapse. On structures like bridges and highways that are constantly in use, detecting these problems before they lead to catastrophe becomes a huge and costly challenge. But not doing so would also endanger thousands of lives. Fortunately, we're already experimenting with ways this material could start fixing itself. And some of these solutions are inspired by concrete's natural self-healing mechanism. When water enters these tiny cracks, it hydrates the concrete's calcium oxide. The resulting calcium hydroxide reacts with the carbon dioxide in the air, starting a process called autogenous healing, where microscopic calcium carbonate crystals form and gradually fill the gap. Unfortunately, these crystals can only do so much, healing cracks that are less than 0.3 millimeters wide. Material scientists have figured out how to heal cracks up to twice that size by adding hidden glue into the concrete mix. If we put adhesive-filled fibers and tubes into the mixture, they'll snap open when a crack forms, releasing their sticky contents and sealing the gap. But adhesive chemicals often behave very differently from concrete, and over time, these adhesives can lead to even worse cracks. So perhaps the best way to heal large cracks is to give concrete the tools to help itself. Scientists have discovered that some bacteria and fungi can produce minerals, including the calcium carbonate found in autogenous healing. Experimental blends of concrete include these bacterial or fungal spores alongside nutrients in their concrete mix, where they could lie dormant for hundreds of years. When cracks finally appear and water trickles into the concrete, the spores germinate, grow, and consume the nutrient soup that surrounds them, modifying their local environment to create the perfect conditions for calcium carbonate to grow. These crystals gradually fill the gaps, and after roughly 3 weeks, the hard-working microbes can completely repair cracks up to almost 1 millimeter wide. When the cracks seal, the bacteria or fungi will make spores and go dormant once more, ready to start a new cycle of self-healing when cracks form again. Although this technique has been studied extensively, we still have a ways to go before incorporating it in the global production of concrete. But these spores have huge potential to make concrete more resilient and long-lasting, which could drastically reduce the financial and environmental cost of concrete production. Eventually, these microorganisms may force us to reconsider the way we think about our cities, bringing our inanimate concrete jungles to life.